Welcome to Lecture 3, Introduction to 2D Lattices. So now that we have some of our fundamental operations defined, let us go forward and use them to describe what a lattice is. So for translation operation, we've already shown that T, and I'm using a bold T here, so instead of using T with a arrow, sometimes it's easier when I'm just typing into PowerPoint to use the bold T, which, as you probably know, is an equivalent way of showing a vector. So bold T here is a vector, and so for translation operation, n, which is an integer, times t produces a lattice. The thing to remember about a lattice is that it's just geometry. You'll see that often people use it as a structure, but actually the lattice is just a geometric thing defined by these vectors, nt, and that's it. If you put an atom at each cell, then you would be producing a structure, and people will misuse this, and we will try to avoid it, but I'm sure we'll, like everybody else, superimpose the two meanings. But this is just to let you know, from a purity point of view, that the lattice is just the geometry related to the geometric points created by translation vectors, and that things like lattice energy actually have no meaning, because obviously geometric points don't have any energy, but you need to put atoms in there, in which case it becomes a structure. So in this class, like all the other ones, we'll definitely err, I'm sure, on the side of calling things lattice, but that's actually the official definition. So to fill 2D space, you can't have only one vector. You need to have two. And there's a very simple argument without getting into complex mathematics. That's another thing that happens, by the way. You'll see often that most of our derivations are geometric. They're geometry. So geometry is very interesting because, like I said at the beginning of this class, the geometry actually can define a lot about crystal systems and narrow things down to very few choices without really doing a lot of solid-state physics. So it's very fascinating. And here's an example. I mean, this is a very simple example, but where to define a 2D lattice, you're going to need at least two vectors. You can see that in the simple geometry rule shown here, that if I have T1 and T1, it keeps on moving along. So I have n T1s that define this one-dimensional lattice, but I want to define it in 2D. And what you'll see, of course, is I can't have T2 be along T1, because actually it doesn't reproduce. If we have the same starting point, in each case, if I define this as the real lattice, these points then are the lattice points. Well, obviously T2, if it's different magnitude especially, and if it's the same as T1, that's identical. So if it's a different T2 magnitude, I actually cannot have it be parallel, because it defines points that don't overlap at all with the lattice points. So clearly T2 cannot be parallel to T1. Very simple geometric proof that that's the case, and therefore the most primitive 2D lattice that we can create is by having a non-parallel T2 to T1. And so as you can see here, we'll have this guy would be 2T1 and so on. And of course I could have over here, this guy would be 2T2, right? If I were to go up here, So this point here would be 2t2, 2t1, right? Because I took two t1s and two t2s to get up there. Okay? So fairly straightforward, primitive 2D lattice with some simple proofs. So now let's just make sure that we understand. Let's go back here 1 second. I want to show something. If we look at this here, we can see there's some fundamental unit in here, right? And of course, this is going to be key, and I know that most of you have seen this before, but that's going to be some sort of primitive cell, right? Because, you know, if I extend this throughout space, I can always define larger cells, but this is some sort of, you know, fundamental unit here, right? And so that's going to be, you know, a really important definition of our 2D space. So we have T1 and T2, and that defines some sort of lattice here that keeps on going, right? Because remember, it's n T1 plus m T2, n and m are integers. And we're going to define this, let's call it, let's make another one of our, actually let's change color. And let's make this motif like that then hangs. Now, of course, when I put a motif in, this becomes a structure now, because now actually, you know, these red points, remember, were just a lattice, but now I've inserted a motif, and it's hanging at every point. So the relationship here is the same, meaning that notice how whatever this is here, this little x, y prime is the same to each point on this, if I drew it correctly. So that thing's hanging on that lattice site at every one. So now I have a structure. And you can see how the pattern could be different depending on, you know, what is there. So for example, let's pick another type of shape. You know, it might be that I have that, and then I have a circle at each point. I'm just making this up. So, you know, oops, I should have drawn this like over there. But anyway, so now I have these two features, right? So if I were to just draw that pattern, all I would see, if I were to look at the structure, and again, sorry for my reproducibility skills here. In space, I would just see this, right? Because the lattice is just a geometrical thing. Okay? So that would be the actual structure that I see for this lattice. Of course, I drew them at orthogonal angles to each other, which I should have. Okay, so lastly, you know, that unit cell, one of the important things we want to do is make sure we have some sort of way to make things consistent. So, you know, I want to show you here that if I have the same lattice, and draw another one, I'll draw that primitive cell again, if I can do it well here. You can see that that may be one primitive cell, but I could draw another one, and I could have that, and that actually would produce a lattice too, because you can see here that basically at every point I can describe the lattice by having this T1 and this T2, and it'll reproduce all the points. You know, I can get to any, that's off the screen here, but I can get to any lattice point equivalently by having this, because remember this one just would be longer and connected back to the point that's down here, right? So this guy would be, you know, T2 prime, right? So all these lattice points can be defined by that, and so therefore we're going to need some rules to define what the primitive cell, and it's actually pretty simple. You need to pick the shortest translation vectors. So you can see here that that T2 is much longer than T1, so this would be the preference. That's why this long one wouldn't be used. And you got to pick vectors that display the symmetry of the lattice. So, you know, you could actually have, for example, we'll find out later, you know, we can have a hexagonal lattice, in which case there's a relationship between this diagonal that comes across here, and that's the primitive cell, which shows a little bit more about, you'll see we have these things that we put here, they're called threefold axes, right? Now if I draw this completely out, you'll see actually that there's another cell that we're going to be able to identify later, which comes on here to the next unit cell, comes over, comes up, and does this. And we'll want to do that to recognize certain things in the future. But you know, this is a rectilinear lattice, it's a rectagonal lattice, and that doesn't actually show the symmetry like the red one does, right? So the red one shows much more about the threefold axes that are inside this primitive cell. So the shortest translation vectors and vectors that display the symmetry of the lattice are going to help define the primitive cell. You know, I've been calling it the primitive cell, and I should be more careful in that, you know, the other more official definition for what we're doing right now is a standard cell, okay? And as I said, you know, you can see that, again, I would have T2 prime here, but that wouldn't work because the symmetry is still displayed by T2, but it's not the shortest one. And so this, and this would be the standard cell. So let's stop there, and we have covered the very, very briefest introduction into 2D lattices, talking about how T1 and T2 can't be parallel, automatically define a lattice, and then we talked about how to create a standard cell.